In this video, I'll discuss on equations of equilibrium. Here we can see two objects, a building and a rocket. The building is standing and the rocket is moving relative to its surroundings. In terms of statics, the building is said to be in equilibrium, whereas the rocket is not. Remember the word relative. If you see them from the planet Mars, both are moving. How to define this in a scientific way? When summation of all the forces acting on an object is zero, then the object is said to be in equilibrium. In other words, if an object is in a complete rest with respect to a surrounding environment, then it is said to be in static equilibrium. For example, a rope used in the tug of war with equal forces from both sides, standing building, books on a table, or a table itself, and so on. This means that if there is a net unbalanced force, then the object should be moving. For example, a rocket or a car or a rope when one is pulling more than the other. An object can't be at rest when the net force is not balanced. Let's see some conditions of equilibrium in terms of force. All four black objects are in equilibrium. The important thing to remember here is the force has magnitude and directions as well. That means the direction matters. For calculation, we normally assume force rightwards is positive in x direction and negative leftward. So this negative. Similarly, the force pointing upward is positive and downward is negative. We can assume the opposite, but sticking with the same rule will prevent you from making mistakes. In this example, there is one horizontal force of 10 kN rightward and 10 kN leftward. So this becomes positive 10 and this becomes negative 10, which means summation is 0 in x direction, and plus 40 upward and negative 40 downward in y direction, which also sums to be 0. Same with the second example. In the third example, there are two 10 kN forces leftward and 20 kN force rightward, which means the sum is 0 with proper sign convention. In the last example with the inclined force, we can see both of them are in the same line of action as in the tug of war rope and are equal in magnitude but acting in opposite direction. Hence they cancel out each other to make the object in equilibrium. Let's convert these understandings in mathematical terms. In real life we encounter three-dimensional space. So we have x-axis, y-axis and z-axis. For an object to be in equilibrium, the sum of all the forces in x direction should be equal to 0, in y direction should be equal to 0, and in z direction should be equal to 0. In addition to 0 forces in all three directions, the object should have net rotation or moment along all three axes should be equal to 0. Moment about y, moment about x and moment about z should be 0. This can be written in terms of 6 equations. Summation fx equals 0, fy 0 and fz 0. Similarly, moment about x equals 0, moment about y equals 0 and moment about z equals 0. For many structures, analysis can be reduced to 2 dimensions instead of 3 dimensions, like a truss or a beam. This means we can effectively reduce the 6 equations to 3 equations. Sum of the forces in the x direction equals 0 and sum of the forces in y direction equals to 0 plus sum of the moment in z direction should be equal to 0 for 2-dimensional equilibrium. M0 means the moment about z-axis should be equal to 0. This z-axis is an axis perpendicular to the computer screen, or a line drawn from your eye to the computer screen. So the golden rule of statics says anything and everything that does not move in this world is known to be in perpetual equilibrium and is obeying three golden rules of statics: summation of fx equals 0, summation of force in y direction equals 0, and summation of all the moments in z direction should be equal to 0. Equilibrium in two dimensions can be further divided into two parts: equilibrium of particles and equilibrium of rigid bodies. A system can be assumed to be a particle when there are no rotational forces or moments in the system. As all forces are acting on one point only, two equations of equilibrium apply in equilibrium of particles. In this example, we can see two people are pulling Christmas cracker. Here the system is cracker and the external forces are pulling forces. Since both forces are on the same line of action, the system does not rotate. Hence, the system can be analyzed as particle system. A system has to be assumed to be a rigid body when there are moments on the system or the forces on the system can create a moment. All three equations of equilibrium apply in the equilibrium of rigid body analysis. In this example, a person is trying to push a tall block from the top. This force creates the rotating moment so that the block may topple. Hence, the block as a system should be considered to be a rigid body.